by continuing the explanation of coefficient of determination by this figure. This figure explains the partition of the total deviation into explained and unexplained deviation of the simple regression model. When we take a look on this line is y bar, which is the mean of the y. This line explains the best fitting of data, which is the linear regression line. And when we look at this is the total deviation of error. This is the total deviation, and this deviation and this total deviation of the error partitioned to two partitions. The first partition is the unexplained deviation of error, and the second one is the explained deviation of error. The first one, by mean, it is unexplained deviation of error, which is the difference between the observation or the actual observation, which is yi, minus the y hat. Y hat is the estimated one, or the forecasted one, or predicted one. But the explained deviation is the deviation between y hat, or forecasted line, and the mean of this line. When we put to this formula, when we look to this formula, we find that the total deviation, which is the difference between any observation and its mean, yi minus y bar, is equal to the sum of two partitions. The first one is the unexplained deviation, yi minus y hat, plus, as shown in this figure, plus y hat minus y bar. When we take the square of, when we take the sum of squared of this formula, we find it the summation of yi minus y bar squared equal to the summation of yi minus y hat squared plus the summation of y hat minus y bar squared. And finally we find that the SST, which is the total sum of squared, equal SSE, which is the sum of squared error, plus SSR, which is the sum of squared due to the regression. Finally, we find that R square, which is the coefficient of determination, equal to SSR over SST over SST, and it is in the same time equal to the summation of y hat minus y bar squared over the summation of yi minus y bar squared. And we know what it means by it. When we look at this example, it is in the reference, we find that the first item or the first variable is x, which is indicates the period from 1 to 10, and the sales during this period is yi, which is 10 item also. It is the sales data over 10 time periods. When we make the time plot or the scatter plot, we find that this is indicates through this plot, which is a scatter plot of sales versus time. And when we make some calculations to find the best fit line, we find that this line is the best fitting line, and the equation of it is equal to y equal 23.33 plus 3.39x, and we find it by finding firstly b, which is equal to the summation of xi minus x bar times yi minus y bar over the summation of x. We will write it, okay? The summation of xi minus x bar times yi minus y bar. This is over to the summation of xi minus x bar square. This is the value of b, which is a slope. Okay, and the value of a is equal to y bar a equal to y bar. So it is the first very important step to find y bar and x bar. So we find the regression equation by this two equations or two formulas, P and E. Okay. The second table we will make is this table. This table will be made to find r squared, where r squared equal to, r square, I'll find the pen, r square equal to SSR over SST. I'll r square, I write it on this slide, r square equal to SSR over SST. Okay, and we know that SST is the total deviation, SSE is the unexplained deviation, which is the difference between yi, the summation of yi minus y hat. But the explained deviation is the deviation between, or the sum of squared deviation of y hat minus y bar. So we find r squared by turning to the next point. We find that r square equal 54%. R square equal 54%. In the case of the sales and time data, the explained SS, sum of squared, is 950.3, and the total SS is 1760, as shown in the table of the previous table. Hence, so R square equal to 54%. Note that we could have also calculated R square as the square of R x y, which is R square equal to R. This is the coefficient of correlation, and we find it before, which is equal to 0.735 square, which is equal to 54%. So there is a 54% of the variation in the sales data can be explained by the straight line model with the time variable. The remaining 46% of the variation is due to random fluctuation. So we should make a very important step, which is the Anova table in our equations. The first column is the degree of freedom. Degree of freedom in regression equal n-1, and the degree of freedom of error is equal to n-m. The total degree of freedoms equal the sum of these two, DFR and DFE. And the second column will be SS, squared, sum of squared. Sum of squared in the regression is SSR, and sum of squared in error called SSE. And the total is equal to the sum of these two rows. MS, or mean of squared. In the first row is MSR, mean squared due to regression. MSE is mean of squared error. Here it is equal to the second column over the first column. And finally we will find if this value which is equal to MSR over MSE. Here it is a simplified Anova table. Here's the degree of freedom in regression equal 1, because there is the one independent variable which is x, and in multiple regression equation this degree of freedom will increase. Okay, so for example, find the linear regression equation and find the coefficient of determination, and find also I don't write it, find also the Anova table. For this example, there's hours studied and grades on exam. Hours studied will be x value, and grades of exam will be y value, which is dependent variable. Firstly, we will plot the data on the scatter diagram. When we plot this data, we will put hours studied as on the x-axis, and we will put grades on exam on y-axis, so we will find there is a positive relationship between hours studied and grades on exam. When x increases, y will increase. This point will be the observations, and we will make a line which is closest to these values or these observations. So this line called regression line, and we will find and use sample data to find this regression line. And the equation of this line will be y hat equal b naught plus p1x, or as we take it in the lecture, we find it y hat equal a plus bx. It is the same, where y hat is the predicted grade on exam, b naught is the y-intercept, b1 is the slope of the line, x is the number of hours studied. Please pay attention, and I'll write it on this slide. The intercept when line cuts the y-axis here. Okay, but the slope means that when x is increased by 1 unit, y will increase by b1 unit. Okay. Please take a look. When we want to when we take a look to this graph, we find that we want to minimize the deviation or the distance between the observations and this line as possible as we can, and we can find it by the equation of minimization of the summation of yi minus y hat squared, which is the least squared method, where yi is observed or actual values of the dependent variables, and y hat is the predicted value of the dependent variable. So, for example, when we take x equal to 3 hours studied, approximately when we by our eyes, when we take a look on 3 and go up, we find it's approximately on the line equal to 69, but actually it is 71. Actually means in the table it is actually observed, but y hat we approximate it by this line. We find it on this line. Minimize sum of the square of deviation between observed and predicted by the least squares method, which is have this formula. And to find y hat, we will follow this table. The first and second column, it is given, and we will make those columns. Please write it on your notes. xi minus x bar, yi minus y bar, we multiply these two columns by each other, and finally we find xi minus x bar squared. And please don't forget to find x bar and y bar. in this slide we find that we find P1 and we find also P node, and finally we find the regression line equation, which is y hat equal P node plus P1x. The estimated regression line equal to 55.048 plus 4.74x. We will use this regression line to predict the value of y for a given x. It is a very important point. Please concentrate on this point. And maybe in the exam I'll put this point into my consideration. Suppose number of hours studies is equal 3. What is the predicted grade on the exam? This is a very important point. I said it again. X equal 3. What is the predicted value of y? I'll substitute x 3 by x. We will put 3 instead of x. Okay, and finally you find y hat equal to 69.268. The second table we will make is this table. We will compensate or make the third column is predicted grades, and we will put the regression line or the estimated regression line equation, and we find it y hat equal to 55.048 plus 4.74 xi, and we will put in every row, in every observation, we put 2 instead of x. We will put here 9 instead of xi. In the third observation, we put 5 instead of x also, and finding y hat. Error. We know that error is the deviation between the observed value and the estimated one, which is equal to yi minus y hat. And we will find the squared error. Then we find the deviation. What is the deviation? It is the difference between yi and its mean, which is y bar. And we find y bar in the first step. We find x bar and y bar, but here we will use y bar. Finally, we find the square deviation. We squared this deviation. All of this table, I make it to find r square. SSE is the sum of squared error. SST is the total of a sum of squared. Okay? We know that r square equal SSR over SST. But how can we find SSR? SSR is the difference between SST minus SSE. SSE, we find it from the table. SST, we find it also from the table. So we can find the coefficient of determination by SSR over SST and we know these steps. I explained it, but we should know the very important points that R square is the percent of the variability in y which can be explained by x. When R square equal to 95%, we find it, and its mean will be there is the 95% of the variability in grades can be explained by the number of hours, and the remaining percent, which is 5%, due to some fluctuations, due to IQ of the student, due to experience, many things. So we can find the Anova table by substitute all of the sum of squares, SSE, SSR. I'm finding MSR, MSE. This table is very important also. Please study it hardly. We can finally make summary to all of the problem, which is y hat equal to b naught plus p1x. It is the estimated regression line. Y hat, we find it by the first table, by finding y bar and x bar and the deviation between them, and finding b, which is equal to the summation of xi minus x bar times yi minus y bar over the summation of xi minus x bar squared. And we find R square, which is equal to SSR over SST. By looking at this graph, we find that the total variation, which is the difference between the observation and y bar and the mean, this is the total. This total divided into two partitions. The first partition is unexplained variation, which is SSE, and the explained variation, which is the variation between the line and y bar. So R squared equals explained variation over explained variation, which is this, over to the variation, which is this. And we explained multiple linear regression. By turning to the forecasting using time series models, we explained this in the lecture, and we will turn to the time series components. It is a time-ordered sequence of observations taken at regular intervals over a period of time. Okay, so the time is a very important factor in the time series. Time series has 4 components: trend, cyclical variation, seasonal variations, and irregular variations. The aim here is to measure the effect of each factor or of each component of these 4 components. Time series model is a description of the relationship between the series and its components. Again, time series model is the description of the relationship. There is a relationship between the series or the time series and its component, these 4 components. The first component, trend component. The trend is the long-term pattern of a time series. A long-term, يبقى the important point here, it is a long term. A trend can be positive or negative. Positive like here and negative like this graph. Depending on whether the time series displays an increasing long-term pattern or decreasing long-term pattern. If a time series doesn't show an increasing or decreasing, if it doesn't show any trend increasing or decreasing, this series will be stationary and the mean. Stationary means scoon. Trend of a time series is the long run changes that its effect appear after a long time period. So it appears gradually and move up or move down for a long time. The population, agriculture, production, time, item manufactured, number of persons and this, number of industry or any factory, number of schools or colleges are some of its examples showing some kind of tendency of movement. Okay, and very important point during this slide is the trend component is the long-term pattern. Time series second component is the seasonal component, the seasonal variation. Seasonality occurs when the time series displays regular fluctuations during the same months every year or during the same quarter every year. This variation will be present in a time series if the data are recorded hourly, daily, weekly, quarterly, monthly. All of these are seasons. For instance, retail sales peak during the month of December. Changes that happen frequently in a specific time, the cycle is less than a year. Here, less than a year. When we take a look on this on these two graphs, we find that, for example, if we make example of ice cream, the sales of ice creams in summer will be increased every summer, but in the winter it decreased during the 1 year. So the cycle here is less than a year. When we look at this graph, we find that in 2004, 2005, 2006, there are 4 quarters in every year, and the cycle is less than 1 year. During these 4 quarters, we noticed that there is a fluctuations, there is incredible sales of ice cream in summer, but in winter there is a decreasing in sales in ice cream. The third component is the cyclical component. Cyclical component is showing that any pattern showing an up and down movement around a given trend, up and down. Up, which is prosperity, down, which is depression. Up and down movement around a given trend is identified as a cyclical pattern. It is the 4-phase cyclical comprising of the phases of prosperity, recession, depression, and finally recovery. The duration of a cycle depends on the type of business or industry being analyzed. The rise and fall of time series over periods longer than 1 year. So seasonal component is less than 1 year. Cyclical component is longer than 1 year. We find this graph indicates that the time period is from 1991 to 2011. Finally, the irregular component or residual variation. This component is unpredictable. Every time series has some unpredictable and uncontrollable components that makes it a random variable. In prediction, the objective is to model all the components to the point that the only component that remains unexplained is the random component. Residual variation have no pattern, and it is the remaining of the previous changes. Factors that can't be controlled, such as earthquakes, floods, and I said in my lecture, COVID-19, these changes can be predicted. This graph indicates that the long-term movement or trend. There is a long-term movement, it is a trend. There is short-term movement, it is divided to seasonal variation and cyclical variation. Finally, the random or irregular movement. It make sudden. And this is also figure which is forecast variation. Here, this is the trend, and we find here this is the irregular variation, earthquake for example. Here it is a cyclical variation, and here it is a seasonal variation. It is up and down, and it is so seasonal is less than 1 year, cyclical more than 1 year. Here when we take a look to this graph, these two graphs, the first one, which is sales of new one family houses in USA, we find the follows. The monthly housing sales show strong seasonality within each year, as well as some strong cyclical behavior with period apart from 6 to 10 years. It is more than 1 year. There is no apparent trend in the data over this period. We don't know the trend. It is increasing one or decreasing. The second figure, the U.S. Treasury bill contracts, show results from the Chicago market for 100 consecutive trading days in 1981. Here there is no seasonality, but an obvious downward trend. We find there is a downward trend. Possibly, if we had a much longer series, we would see that this downward trend is actually a part of a long cycle. But when viewed over only 100 days, it appears to be a trend. In these graphs, the Australian monthly electricity production shows a strong increasing trend with a strong seasonality. There is no evidence of any cyclical behavior here. But finally, in the final graph, we find the daily change in the Dow Jones Index. It has no trend, seasonality, or cyclical behavior. There are random fluctuations, which don't appear to be very predictable, and no strong patterns that would help with developing a forecasting model. Thank you. Please make notes to this lecture and study it hardly. Thank you, my students.